Hi everyone, my name is Saad Qureshi and I'll be your physics teacher this term. I hope everyone's doing well and everyone's excited to be in this class. Unfortunately, due to reasons beyond my control, I'm unable to join you in the classroom, but the show must go on. I welcome you wholeheartedly to this classroom and I hope I can join you soon so we can get to know each other and we can learn new things, amazing things. And without further ado, let's start with Unit 1. Well, it's more like Unit 0 by its introduction to physics. Um, and the entire reason of having this presentation here today is more to do with that you get a chance to refresh things in your mind that you may have used before but might have forgotten or you did not learn them quite well beforehand. But I'm here to guide you through and help you through and enhance your learning because that's what's really important. Before we start with the actual chapter, uh, I would like to I would like you to do is to record any slide number that we're on so that you may if it comes to if you have any problems because this is going to be a video recording, so if there's any problems that you encounter, you just send me an email and I'll try my best to reply to you as soon as possible so we can help you in that learning process that I was talking about a few moments ago. So, starting on Introduction to Physics. So, before we start with physics, we're all know that physics is a branch of science. So, what is science? What do you, what does the word science really mean? Going through Google, I found a quick definition because we know we use this word quite often, but we never really, you know, I personally have never really sat down and looked at the definition of science. Currently, I might have looked at or I might have read through it when I was your age going through school, but I haven't really. But what it is, it's a method. It's a method that allows you to study the physical world, right? So it could be anything. The physical world is made up of. Oh, there are so many things. So if you just sit down, think about it, science can apply to everything, right? So, like I said, it's divided into multiple categories. A few of these categories, a few of these really important categories, include life sciences, which allows you to basically deal with all living things like plants, humans, insects, animals, whatnot. There's earth science, which has to do everything that is on this planet Earth and around it. So space, it's the study of universe. Science does that. And then there's the physical side, the physical aspect of it, which is to do with matter and energy. Can these overlap? I don't see why not. A few examples could be biophysics, biomechanics, robotics. Do you know what these terms are? What I would like you to do is search a few of these terms and define these, find a few others, define those, how those are associated, how they form, or how are they part of science, and then submit it to me. You will see an assignment on Google Classroom, and once this class is over, you go back and you submit it to me. So physics. What is physics then? We already said it's part of science. And if it's physical science, then it's got to do with matter and energy, right? So what if you look through your syllabus, I've recommended a textbook which is sitting on the benches behind you. It's the whole physics book. Um, so the definition in that is that it's a branch of science, right? Physics is a branch of science. We know that. But more importantly, it is a study of the physical world, same as the slide before, right? These are kind of book definitions. What I rather would like to add to it, or what I personally feel about physics, is that it's to answer the question, why is physics important, right? So before you try to define what is physics, you should think about it in terms of how physics is attached to science, right? And then why is physics important? And therein lies the definition of what is physics. And this is something that I came up with, but I may be wrong. I might be missing something, but I'll be happy if you can correct me and if you find something better on the internet. So this is part of your other assignment, or the assignment continuing the previous assignment that you had to do with biophysics and biomechanics. What I say is that physics is a set of laws, rules, procedures that describe or provide you with the tools that are necessary or that enable you to understand the physical world that surrounds us. So it could be a set of equations, it could be a set of laws. So by set of laws, let's talk about thermodynamics. Does anyone know what thermodynamics is? It's to do with temperature, heat, and energy, and we'll get into it. But a basic law of thermodynamics is that if I were to take a hotter object and place it next to a cooler object, or let's say in summer, if I take a cube of ice, drop it in glass, what will happen? The ice will melt, right? What's happening? The water will get colder, right? Or whatever that temperature it was at. But necessarily water is hotter than ice. So what's happening? Water is transferring its energy to ice. And in turn, ice is melting. What's happening? So as energy is being transferred from that glass of water, or from that water into ice, because there's transfer of energy going on, and if I don't know if you've taken science at this point uh, or not, but essentially you're decreasing the energy or water. The total energy of the water is decreasing, and that's being transferred into ice, which in then turn is being converted into ice. So as the energy is decreasing, the temperature is decreasing, and on the other side, ice's temperature is increasing, but that's melting, and then it dissolves into water. What happens next? There's diffusion going on. So those molecules will move as they get energy, as they get mixed into water. They all continue to mix, and that's a rule. Now, what happens what you can say, the other way does not happen. So the glass of water will not turn into ice if you were to just drop ice cube into it. And that's a law. So the energy transfer in this case is from a higher number to a lower number. It won't become from a lower number to a higher number. That wouldn't happen. So that's the law. So it's all of these things that are happening. Or in another case, if I were driving a car and I hit a tree, the natural thought process is that the car would stop. On the collision, the car would stop. Or it would continue a little forward, but depending on where the impact is or what I've impacted. Or if I were to take the car, drive it into a wall, what would happen? The car would remain come to home. It's unlikely the car will start will keep on continuing to move, right? So these are some laws and rules that follow that the trend that we've observed, right? So it's a set of laws that we've created from observance. But then physics itself is not just physics. Physics. There are many branches within physics itself. A few of these are mechanics. There's thermodynamics, like I mentioned before. There's vibrations and wave phenomena. There's optics to this, and then there's electromagnetism. Mechanics is it's all to do with motion based and interactions and forces and whatnot, right? Thermodynamics is to do with heat and temperature, so freezing processes, engines, refrigerators, your air conditioning that you've got in this building, so all of those things. Vibrations and wave phenomena is more to do with what's repeating, right? So think about dampeners in your car, shock absorption in your car, or think about uh, the vibrations in your laundry machines at home or dishwashers at home. All of them, those things are being dampened somehow. Or if you were to move it on to life sciences, think about there's a heart beating within your chest, and that's good to do some sort of vibration because it's a repetitive motion, right? So, and that's being dampened, and this is all those things. And there's optics. I wear glasses, so optics help me to focus on things. That's using the understanding and laws of physics to do that, and it's a branch of physics then. Electromagnetism. You've got your Chromebooks open. You're listening to me. Somehow that's all electricity. So speakers, if you're using headphones or if you're using the speakers off your laptop, which I don't recommend you do because you're going to disturb everyone else. But essentially, what you're doing is that electricity is being pumped through, and there's magnets, which causes vibration. And we'll get more into this, but essentially that's how sound is being produced. And sound is a wave format, and those waves are traveling into your head that are vibrating your eardrums, and that's how you're hearing sound. Right? That they're well, that vibration is being transferred to your brain through neurons. What are neurons saying? They are carrying electrical energy. Electrical energy is being carried inside your body because you've got positive and negative particles at the end of each neuron. So the physics is everywhere. What I'm trying to get at is that physics is everywhere. So why is physics important again? Well, we just went through it. It's part of everything. Now, what I would like you to do is think of a few examples, think of a few everyday examples where you're utilizing physics. We went over a few of those, which was, for example, a car. Um, we talked about washing machines. We talked about how within yourself you're using physics or it's your physics is being utilized. But what I want you to do is take a few everyday examples, list what are the different processes that are going on and what branch of physics it might or what branch of physics might be involved in it, right? So and try to be specific. Try to list as many as you can. You've got about 5 minutes to do it. So this is your activity, and this will go into your daily activity workbook. So time's up. Moving on, like I said, you're to list down a few everyday examples where you're utilizing physics, right? I wanted you to list those examples, try to write down what the processes involved were, right? And then I wanted you to relate those to the areas of physics that we just discussed, right? Some of the examples that I could come up with while we're working include, obviously, well, there's a car, then kettle. I like to drink tea, coffee, so I've got a kettle in there. Then I've got my phone. That's an important part of everyday life now. You've got your stove. You do that for cooking. There's lenses, and there are mirrors, and all of those things that come into it. There's light. Light has for physics. Uh, those last three might be connected, but more or less it's a part of your everyday life. Right? Then, so here's a model of Porsche. Um, and there on the bottom here you see there's a chart which lists all the more of the five different branches of physics, which is including mechanics. There's thermodynamics, there's vibration, wave propagation, there's optics, and there's electromagnetism. Right? So what I could think of as well, there's mechanical part or mechanics aspect to it. The mechanical that goes into the tire movement because remember it has to do with friction forces and weight and whatnot. So there's weight associated with the car that it exerts on the ground, whether it's due to gravity or not. Then there's friction with the tires. There's friction with the air, which would resist the car's motion. Right? Then there's friction within the engine itself. That's why you add oil to it to lubricate it. So there's less friction, so the pistons can move quite easily. Um, so there are all of those things. Moving on, you've got thermodynamics. That thermodynamics is an essential part uh, of your car. It could be within the cabin itself, so you've got air conditioning, or you've got heating, or you've got so there's thermodynamics happening there. Then there's thermodynamics within the engine. You have to because you're burning petrol at this point, or talk about electric cars as well. There's thermodynamics acting there as well because you're using up batteries. They're going to be discharging. That means they're heating up. So you've got to have some sort of added cooling. Now in your petrol engines or gasoline engines or diesel engines, you've got active cooling by or liquid cooling where you're circulating water at a coolant mixer throughout or pumping that through the engine and that's being cooled by your radiator which is sitting right in front of the car. Uh, in other ways, in electric cars, I'm thinking it might be liquid cooled. It could have radiators. It could have heat sinks. They're different things similar to what you've got on your computer as well, right? There are vibrations. So as you're moving onto the car, moving on the road. Roads usually uneven, quite uneven around here, especially last year when they were working on the road. You've got shock absorption systems, suspension systems within your car, which allow you to move over those bumps and to not feel those vibrations as much. Then there's sound deadening provided by the carpets within your car or that the material that is being fitted into the cabin so they all absorb vibrations so that and sound noise so that you don't hear it as much, right? Um, then there's optics. Obviously, you've got light coming through your headlights, tail lamps, indicator lamps, and there's rear view mirrors. There's glass. There's glass that doesn't really, bend the light too much. So there's special type of glass that you're using within the cars. Remember, there's electromagnetism, right? You've got batteries, you've got audio equipment, you've got your phone chargers, you've got all of those things that are sitting into the car. So they're all using physics. Kettle, right? What could be in the kettle, right? So there's mechanics. Or you pick it up, you pour water out. You've got water coming out. There's friction associated with it. There's intermingling. There's friction within the water itself. there's friction within the water and air, because if I were to pick up the kettle, raise it really high and then pour it, the column that is coming out of it, or the column of liquid that's coming out of it, will break apart. It'll create those little blobs that will fall into your cup. Hopefully you're pouring into a cup, but essentially there's that thing happening. Then you've got thermodynamics, you're heating up water, right? So you're adding energy to the system, which is raising the temperature of water essentially to 100 degrees Celsius, which then allows the water to boil. We've got vibrations and wave propagation, because you're adding energy to water. It's going to start moving. That's what happens when you're boiling this water. There's bubbles escaping, or it's not bubbles, it's more to do with the water that has converted into steam that is escaping in the form of those bubbles, right? Um, and there's optics within that little glass that enables you to see where the water level is, and then there's electromagnetism. Obviously, there's some sort of circuitry involved. Um, don't know about if there are any magnets in the kettle, but essentially what you're doing is you're converting electrical energy to heat energy, right? So there's that part going on. Phone, you carry this every day. You can't live without it. It's got everything, and there's the mechanics. Your phone is assembled into a single body, right? It's being held into place by screws. Screws are holding it together by friction. It's a friction that doesn't allow it to move. So you're banded down really tightly. You screwed it into frame really tightly, and that's the friction part that's holding it together. Then you've got your thermodynamics. You've got a battery, right? So let's say you're playing Fortnite. It's been banned by Apple, but let's say you're playing Fortnite, or you were playing Fortnite on your Apple phone or your Android phone, and you'll notice that it gets really warm. That's thermodynamics. That's your processors generating heat. Your battery is being used up. There's charge being delivered to the processor because it's being actively used. That's generating heat. So that's thermodynamics, right? Then you've got vibrations. Your speakers, they work on the vibration phenomena because it's generating sound waves. We've got optics in your camera, in your screen, but mostly in your camera. You've got a set of lenses. Light will pass through, it'll produce an image that's read by the processor, and that's generated on your screen, and you take a picture or a video or whatnot, but essentially it's going through those optics and the lenses, making sure how much frame you can capture. I won't go into these things, and you can find a lot more things into it. And then the electromagnetism, it's electrical circuitry, right? So speakers are using magnetism and electricity. There's batteries using electricity. There's circuits. So now everything's going on. So use physics in a lot of ways that we don't realize, or we don't notice, or we tend to forget about during everyday events. It's essentially science. So without science, we won't be here. I like to say that much. So next part is scientific method. Before I start with this slide, I'd just like to remind you all that if you've got any particular questions that you want to clarify, just send me an email and I will try to respond to you as soon as possible. Whether it's in class while I'm not there, and hopefully I'll be able to be with you soon. So what could be the scientific method? Think about it. We've got, try to write it down. You don't need to correct it. Um, I'm going to mark your assignments. I'm going to grade them, but I'm not. I just want to check where you're standing, right? So there's no right or wrong answer at this point. So what could be the scientific method? Just think about it. What we've been talking about so far is that science is everyday life. What is physics? Why is physics important? It's a set of rules and regulations. If physics is a set and it's based on a set of rules, regulations, laws, and procedures, right? Essentially, science is built onto that part because physics is a branch of science. So science is, again, is a set of laws, procedures, rules. Who came up with science? Whatnot. So these laws and these procedures and these rules, they were all formed because somebody observed them and wrote them down. So, for example, if you heat up water, it will get hot. That's a procedure. Well, that's a law that it will get hot. But the procedure is that you're burning fire and you're putting water on top of it, and then heat is being transferred into it through convection or radiation or conduction, whichever way the pot has been laid onto the fire. So those are the procedures to get to or to observe that law, right? Or that rule that was formed. So they're all observations. That fire is hot. If you put a pot of water on top of it, it'll get hotter, right? So what could be the scientific method? Or what would you do? Essentially, let's rewrite the question. What would you do if I were to ask you that, or if you wanted to test out a new theory which you think might become a law or might become a rule in the world of science? Well, the very first thing to do is that you define the problem, right? So you say that this is something that you've encountered and you notice that nobody's talked about it, so that's you defining a problem. Then you do your research on the problem. Is there a solution? Does anyone know it? Or or doesn't anyone know about it? Has somebody done anything about it? And based on your research or your problem definition, you will define a hypothesis, right? Or your hypothesis will form that, okay, this is a problem that no one's worked at, or this is the way that things should be. For example, let's say um, if I were to charge my phone with a 10-watt charger than a 5-watt charger, or a 5-volt charge, sorry, it would charge it faster. If nobody's done that, that's your hypothesis, right? So you will do hypothesis testing, where you would basically go through different voltages of chargers and you'll connect it to your phone, and if it charges faster, then what you've done your data analysis, and then you've come to your conclusion. But before you can tell everyone, hey, this is something that I found, what you need to do is you need to get it through a peer review process. And what a peer review process does is it's something that it's a group of people who are working in a similar industry. They will check the credibility of your work, and if they find it correct, they'll approve of it. And once they have approved of your work, basically that means that you've found something new. And if it's something new, that would most likely form a set of laws or a set of rules and procedures in the world of science. That's what you're seeing every day with whatever is happening in the scientific world. For example, it could be graphene, which is a material that is lighter than the air, or if you're talking about Tesla's new battery technology that they're coming up with, which can store more energy, or there are battery technologies that people are coming up with that charges really fastly or faster really fast compared to the ones that we're using these days. So there are a lot of things that people are coming up with, and that's rewriting the rules and laws that we know within physics realm or the chemistry or biology or, well, speaking broadly, in the entire science world. One last thing that you need to do as whichever field that you go into is that you need to reduce bias. Bias is something that might come into work, has personally affected me when I'm working at ED. Um, when you tend to favor something over the other, because you might find it easier, or you might find it that this is something interesting. This is something that no one's done before, and you want to do that, or You're treating data, you negate some data based on, well, this doesn't fit here or that way. That's just bias. You shouldn't do that. You should have everything inclusive. What if you're using a set of equation, it should and that should produce positive numbers, but you came across a single negative or double negative number, I mean two negative numbers, you should include those in your data set. That's what reducing bias means in very simplistic terms. Moving on to measurement. How do you measure something? What are units? Could you state a few examples? And what I would like you to do is just jot down a few examples on your little worksheet that you've got going on. Again, there are no wrong answers. If you don't know the answer, just write, I don't know the answer, and I'm fine with it. And then, is there a standard? Do you know of any standards that are used for measurements? For example, the imperial system or the metric system, all of those things. Moving on, we've got types of units, right? So we've got, like I said, we've got an imperial system, and then there is System International, or SI, which was developed in the 1960s. And almost every country in the world uses System International. I believe there are 3 or 4 countries that are not using and are still stuck with the imperial system. And there is a particular reason why SI units are so special. Essentially, that it has got to do with the system of tens, right? It uses a system of tens. And what do I mean by the system of tens? Essentially, you can divide everything or multiply everything by 10 to move to a higher or a lower denomination of those units. So, for example, you've got deca, you've got hecto, you've got kilo, mega, tera, giga, all those things. These are the higher denominations. So you can basically add that factor to it, to a number. You can just write. So if your computer has 128 gigabytes of memory, right? That means it's got 128 times 10 raised to the power of 12 bytes of memory. And within a single byte, you can store, I cannot know, I don't know from the top of my head how much data, but essentially that is how much data you can store within your computer, right? On the lower side, you start reducing from deci to centi to milli. Now, millimeter is something that you can observe with naked eye. Micro, I don't think so. I'm not so sure, but essentially micro, then you've got your nanoscales, machines, all those things, pico, femto, then these go on to the molecular and atomic levels as you keep going lower. Now here what I have for you is a video which is to do with scale of work. It's on YouTube. There's a link embedded into this. There's another part to do with measuring techniques. This video I could not really uh, embed into PowerPoint. I don't know why it wasn't working. So I'll pause here and add this video and let this play. Or if you could type this link up and then play it on your Chromebooks, and once you're done playing, come back to this PowerPoint. I think this is about 7 minutes long or so, and this is to do with measuring techniques. Once you come back, we will talk about measuring techniques a bit more.
You'll never, ever get your head around how big the universe is. Don't go there, it's just vast, it's enormous. There's no way a human mind, I think, can actually comprehend the true immensity of the universe. We're happy with the size of an elephant, or the size of a tree, or maybe even the size of Durham Cathedral. But I think if we go beyond that, then our brains just start to run out of gas.
It may be difficult for our brains to comprehend, but that hasn't stopped astronomers endeavouring to measure the distance to the stars. One technique is to use a phenomenon called parallax.
Everybody can actually experience parallax for themselves. If you hold your thumb up and close one eye, you can see that your thumb appears to be in a certain position relative to something behind your thumb. But then if you open that eye and close the other eye, you'll see your thumb appears to move relative to the object behind.
The same thing happens when we look at the stars. When we look at a relatively nearby star from the Earth, it appears in a certain position relative to the other background stars. 6 months later, when the Earth is on the opposite side of the Sun, the same star will appear in a different position relative to the background. Like opening and closing one eye then the other, the star appears to move, and by measuring this apparent movement, we can calculate the true position of the star. An alternative method of measurement is to use certain stars in the sky known as standard candles. We know exactly how brightly they shine. If we can therefore measure how bright they appear to us on Earth, we can calculate how far away they are. The dimmer they appear, the further they are from the Earth.
So the nearest star to the Sun is Proxima Centauri, and that, it turns out, is 40 trillion kilometers away. That's 40 million kilometers away from the Earth.
Such numbers start to become incomprehensible, and that's why astronomers have adopted an alternative unit of measurement for such vast distances, the light year.
A light year is the distance that light will travel in 1 year. If you imagine light moving around the Earth in 1 second, so in that time, light would travel around the Earth over 7 times. So that's fast. The speed of light is 300,000 kilometers a second.
So 1 light year is about 9 million kilometers. The speed of light also leads to a curious consequence when we stare at the stars.
So the light from the Sun takes 8 minutes to get to the Earth. That essentially means we're looking into the past. We're looking back at the Sun as it was 8 minutes ago. So if the Sun was to disappear right now, we wouldn't know for 8 minutes. So a telescope, if you like, is a time machine. We're looking back in time, and the further the object is away from us, the further back in time we're seeing it.
Our Sun, like nearly all the stars we can see with the naked eye, sits inside the galaxy we call the Milky Way. But our galaxy is not alone in the universe.
Not everything you can see in the night sky is actually in our galaxy. It turns out that some of those faint dots are in fact other galaxies. The furthest object you can see actually with the unaided eye is another galaxy called Andromeda. The light from that galaxy has taken something like 2.25 million years to get to the Earth. So if you imagine if we reverse the scenario and you're looking at the Earth from Andromeda with a very powerful telescope, you'd see no signs of cities, no civilization, no Great Wall of China. You might be lucky enough to see 1 or 2 sort of early humans hunting around on the African plains for their dinner, maybe.
Astronomers have always wanted to see further, using bigger and better telescopes to try and find out just how many other galaxies are out there. Until finally, we pointed the Hubble telescope at what at first appeared to be a very dark and ordinary patch of the night sky.
If you imagine holding up your finger with a grain of sand on it and looking at the patch of sky that grain of sand blocks out, that's the field that the telescope zoomed in onto. And what the telescope saw was incredible.
Every single speck of light in this photo is a galaxy. 10,000 galaxies in a patch of sky the size of a grain of sand held at arm's length. If this tiny patch of sky is like every other, then we can calculate how many galaxies are out there.
The visible universe contains around 100 billion galaxies. Each one of those galaxies contains around about 100 billion stars. That means the visible universe contains something like 10,000 million stars. That means there are more stars in the visible universe than there are grains of sand on the Earth.
The light from some of these most distant galaxies has taken around 13 billion years to get here. That's light travelling at 300,000 kilometres a second. The visible universe stretches around 13 billion light years from the Earth.
So we've said the universe is big. I'm going to try and give you some idea how big. Imagine the Earth as a grain of sand. If that was the case, then our solar system out to the orbit of the planet Neptune would be as big as Durham Cathedral. So now let's imagine we take our solar system and we shrink it down to the size of this grain of sand. Then our galaxy, the Milky Way, would be 1,000 times bigger than this cathedral. So now we take the Milky Way galaxy and shrink it down to the size of the grain of sand. The cathedral would be the entire visible universe. The universe is big. It's really big.
So I hope you enjoyed the video. What this slide is showing you now is that there are seven base units. Now these 7 base units include the distance, which is measured in meters in the SI system, time, which is measured in seconds, and I believe that is consistent whether you are in the SI units or the imperial units. There's mass, which is kilograms in the SI system, or pounds in the imperial system. And there's light, which is measured in candela. I still have to come across in my life when I'm going to use these units. I haven't used them. That does not mean that I will not use them. I might use them. And there's current, measured in amperes. There's temperature, which is measured in Kelvin in the SI unit system. However, what you would commonly find across is that we're using Fahrenheit in the United States, but then there's degrees Celsius in the rest of the world. Now, degrees Celsius is more to do with what I believe, and I haven't looked this further. Please correct me in the worksheet that you're working on. That degrees Celsius essentially defines or is based on the freezing point and the boiling point of water, which is 0 degrees Celsius and 100 degrees Celsius respectively. And essentially, since 70% of Earth and 70% of our bodies are made of water, it would be understandable if you were to base your temperature measurements on water, because then it's easy to link that, okay, 0 degrees Celsius, you'll find ice, right? 100 degrees Celsius, you'll find water boiling, which is going to burn you really badly. So that's something called temperatures in SI units is measured in Kelvin, and that's got to do with the absolute zero, where everything would become static. Even the motion of electrons around an atom, they would not move if you were to reach 0 Kelvin. And then there's the amount of substance, which is mole, right, or molar mass, which I believe you might have worked with in chemistry or science or whatnot. But those are the 7 base units. And using these 7 base units, then you can come up with different units. Now, again, this is an exercise for you to do. You've got about 5 minutes, as before, to go through and convert the following. You may use Google if you want to. If you don't know, if you don't want to use Google, you're welcome to try to convert them yourselves. But convert miles to kilometers, kilometers to meters, miles to meters. Then see what that scale is. Then Fahrenheit to Celsius, Celsius to Kelvin, and then Fahrenheit, degree Fahrenheit to Kelvin, right? And see how different, or it might be difficult to convert Fahrenheit to Celsius. I hope you realize that, but it's relatively easier to convert Celsius to Kelvin and whatnot. And then you can do seconds to hours to days to years, or then seconds to microseconds and nanoseconds. And please use the chart that you saw before. The presentation will be available on Google Slides, so you can use that and you can have that open and use those unit denominations, for example, 10 raised to the power 3 or 4 or 8 or 9, whatever, to state all those microseconds and nanoseconds. You don't have to go ahead and write all the zeros and count the zeros. Right, we're already 4 minutes in. I just wanted to fill in this gap during talking. And if you need a bit of extra time, please do take so. time's kind of up, but you can have another 2 minutes or so to work on it since I was talking beforehand. Right, so I think that's ample time for you to go through this. You might also want to do some calculations with mass where you're converting kilograms to tons or tons to pounds and all of those things, or stones even, because that's at one time was a unit of measurement. It still is in some countries where they measure weight in terms of stones. I think that's about 6 something kilograms, nearly 7 kilograms for a stone. But that at one point was being used as a unit of mass. Now what we have here is another video which is to do with how important it is to measure units and convert them and being consistent with your units.
Road signs in miles, vegetables in grams, beer in pints, and wine in litres? Measurements in the UK can be confusing. It's a mix-up of metric and imperial. But Britain's exit from the EU, expected in 2019, is reviving a push to move back entirely to the imperial system. Will the UK tag along with only 3 countries that still use feet, inches and gallons? Or will it follow Europe and use litres, metres and kilos? Or will Britain continue using both systems, the way it does now? Either way, mixing scales, weights and measures has caused problems over the years. Here are 3 measurement mishaps.
We have ignition and we have liftoff of NASA's Mars Climate Orbiter as we continue to explore the mysteries of the red planet.
It may have taken off all right, but in 1999, NASA's $125 million Mars Climate Orbiter disappeared.
We have a serious problem with the Mars Climate Orbiter. We may, in fact, be facing a loss of mission.
An internal review found Lockheed Martin engineers used imperial units such as feet, pounds and inches in the navigation software. Meanwhile, NASA navigators use metric measurements. That caused the spacecraft to fly too close to Mars, where it is believed to have burned up in its atmosphere. In 1983, an Air Canada plane ran out of fuel in the middle of a flight due to a metric mix-up. A malfunction on the fuel indication system forced the ground crew to manually calculate how much fuel was needed, but the fuel was measured in pounds instead of kilograms. That caused the plane to run out of fuel halfway through its planned route. Fortunately, the pilot managed to land safely at a Royal Canadian Air Force base, and none of the passengers and crew on board were seriously injured. A Tokyo Disneyland roller coaster derailed in 2003 due to an axle error. The specifications for the coaster's axle had been changed to metric units a few years earlier, but in 2002, the old documentation, based on imperial units, was used to order new parts. Since the axle that was ordered was smaller than the proper design specs, it broke. Luckily, none of the 12 riders were injured.
Now next what we're going to talk about is a little bit about accuracy and precision. But before we start working on accuracy and precision, what I would like you to do is, it should have been released by now on your Google Classroom, but for the remainder of the class, which I think is about 20 minutes or so, we will start working on a little assignment, and it's got to do with graphical details on how to read graphs. And this is before we dive into graphical techniques or visualization, data visualization techniques. So I'd like for all of you to go into your Google Classroom, go to your assignments page, and look at the assignment that's been released, and work on it on your own. Again, if you're unable to do it, just write it down on the side. I believe you've got all stylus-based Chromebooks, so you can write that you were unable to work or you did not understand it. And once we go through the visualization techniques, you'll have time to re-go through them. And I'll do a grade for this assignment, and then I'll improve your grades once I've graded them. So you've got some time on that assignment to work for the rest of the class today. And once we come back tomorrow, we'll start working on accuracy and precision. Thank you.